Yes, in September. Don't worry, I just stopped as well.
You can just add another side with the other side. Actually, the other side.
Not really, but I think this
Okay,
is
sorry.
kind of working.
Maybe, yeah, this is gonna work out.
So we're now recording?
I think we're recording as best as we can, so yeah. That's it.
Cross his nerves and that's actually, you should be okay, right? As long as it's
Yeah, it's basically mirroring together. This is unfortunately OBS.
Sorry.
But yeah, that basically though, what it is, that's on your screen is that of the rest of the screen. Good to go? Really chopsticks.
So welcome everybody to MelbJVM for September. I'm just going to hop straight into it. So today our guest speaker for the month is going to be Sukin. He's a full stack DevOps developer, a full stack developer from Shine, and he's going to be talking about some really cool optimizations that the JVM does, especially with the compilers, CLI and C compilers. As usual, a quick thanks to Akenex. They've been really awesome with the venue and the food and the beverages. They're a sponsor. Dotpost is for the PDF and name tags creations, and for the organizers who keep coming every month and helping us out. And of course, to all of you guys who keep coming also. Hopping into the news, this is actually the last meetup before Java 9. So it's like 20 days, less than 20 days, Java 9 is funding out. I think Java 9 build 181 was the first RC cut. It didn't have any security 1 defects in it, so that's a good thing. Or is it not have defects?
It took long enough, so
yeah, it's about time. The whole jigsaw madness. Yeah, Oracle is also thinking about dropping their leadership with Java EE, so they want to hand it off to some more open source community organizations like Apache, for example. So that's been quite interesting. There's also the formation of a OpenJDK vulnerability group, so they're kind of behind the shadows and they'll be working on finding vulnerabilities in OpenJDK and contributing back in kind of stuff. Really awesome. And there's been some talk around incubator modules, which will basically allow you to try unfinished APIs like the HTTP2 client for Java, which will be coming out soon, possibly Java 9, Java 10 also, and it will be using some of the jigsaw features.
HTTP2 client instead?
HTTP2.
Yeah, that's Java 9.
Yeah, cool. In terms of events, Java 1 is happening October 1st to 5th. Is there anyone going from the crowd here? Not seeing any hands up. That's cool. And then other things, the tier index, which actually does a rating on languages and their usage in GitHub projects. Java is still number 1, but it's actually losing popularity, and it's had a bit of a slump in recent times. So maybe we can hop back into some normal Java programming and lift up the popularity again.
So was it Kotlin made a big jump?
Not as much as you'd know. I can't remember what the number was because the tier index didn't have Kotlin numbers before, I think.
Yeah.
But it's made a bit of a jump given Google's recent news from Google I/O this year, where they finally adopted Kotlin as a language and officially supported it for the Android platform. In terms of releases, ByteBuddy 1.7.2 is out, so if anyone's using that, you might want to hop on some new version. I can't remember the features that come out for it. Yeah. And we put this up last time, but just to sort of reach out, is if anyone's interested in doing a Java 9 hack night, given it's coming up really soon, if there are any ideas, if anyone wants to even try a feature of Java 9 and present on it, please reach out to one of the organizers. We're not some friendly and smiling and say hi to us. Or even if you have your own idea, feel free to reach out. As usual, we're out on social media. All of our videos go to YouTube eventually, so if you need to reach out to us, we've got Slack, YouTube, Twitter, Facebook, all that stuff, feel free to reach out. And next one, Java Now launch, very exciting. We're going to have Chad Harris, who's actually spoken with us before. He's a really cool speaker. He talked on GraphQL last year. And he'll be talking on property-based testing. And that'll be on October 4th. Just keep your eyes out for the meetup notification, and we'll have news as soon as possible. And let's jump straight into it. We'd like to welcome Sukin up to the stage.
All right. Good evening, everyone. You all can hear me okay? All good? All right, let's just start. With Java performance improvements using Mystic Arts. Any Doctor Who fans over here? Oh, that's few. That's good, that's good. We did have a bit of a slow start today, so, Java and slow start, why not? So it's warming up now. We're going to get there soon. So there are, Java and performance is a complicated topic, right? I mean, there's been always complaints about performance with Java, and there are many dimensions that actually contribute to these performance issues. And then, there are because there are these different dimensions, you have to jump into them to fix them. One of them is memory leaks. How many of you have looked into the heap dumps of gigabytes, trying to figure out where the memory leak is? Yeah, that's good. It's awesome, isn't it? You just feel the whole day is gone into looking at all these objects that doesn't make sense. And if you're running with, all the other, running on a server, a Tomcat, you'll get all those classes and objects as well. Yeah, but it's a hard task, but we have to fix the memory leaks. And what memory leaks are is basically there's this heap just filling up with these objects which garbage collector is not able to clean up because there's references, and over time it will take more time to run through garbage collection cycle. Eventually it will die. Either it will go, hey, I can't clean up anymore, or your heap is full and the process can't get more memory. So you get the out of memory exceptions. Second one is fine-tuning garbage collection. So this, I feel every application is different in Java, right? Because it has a different profile, different path your code is executed in, different way the objects are allocated. They have a different life cycle. They don't have always behave the same way. And for the same reason, if they are not behaving the same way, you want to fine-tune your garbage collector so that it is actually suited for your application the most. I work with, I've got a colleague over here, I've worked with a company before in real-time systems where having a full GC is like a end of time, like having full GC and pauses is not good. And that's true for all the financial trading applications or any other real-time applications. So yeah, you want to investigate and fine-tune it to your application. Improve ORM performance. So this is ORM, object relational mapping. We use databases everywhere. We go make a trip, and then someone came up with the idea of, oh, you know what? We just query on the class. Why not? It's just going to give you everything. Going to perform joins for you. Going to perform unions for you. In some cases, I've seen that has led to a lot of performance issues. You build all these complex models and entities, which then are resulting into a lot more joins and unions and everything, which means your ORM is actually always busy querying, getting data, converting it, mapping it. And at the end, you find that the service only uses one attribute. And you go, oh, seriously, you were calling everything performing. So in worst case, in my experience, it's been 13 unions and 17 joins to get one value. Yeah, amazing. So yeah, you do want to find out where your bottlenecks are. And if you are in enterprise application, you want to fix them with improving the ORM performance. Inefficient code, well, there is always going to be some code that's inefficient. Now, when I say inefficient, is not like how you write your for loops and things like that. It's just these days we call all these microservices around the world. Everyone likes writing microservices. You just call, hey, give me this user information. and then after 5 lines you go again, hey, give me this user information, but you haven't done anything. So that sort of inefficiencies I'm talking about. Even though it's not part of Java, but we do write and call these without realizing what we have, and that's inefficient code. So you want to find those bottlenecks and fix them. And last one. So this is like probably the mystic realm, Doctor Strange style. So it's just in time and code crash. So this is where Java engineers, VM engineers, have gone, everyone is incompetent programmer or developer. They're going to write code that's just not good, but we are going to do things to it, make sure it is optimized. So this is like a sort of not something we do it on a daily basis, not something we sort of go and look at the bytecode and anything. So trust me, we are not looking at bytecode today. All right, so I'm going to show you guys something very quickly. Just need to. All right, so I have a class over here, very, very simple. It's an introductory class. It has an allocate method over here. All we are doing is there is a for loop that runs 1,000 times, and for each iteration, it's recording the time taken to allocate 1,000 objects.
Sorry, so can you make that a bit larger? Can you zoom something?
Is it better? No? I don't know if it's.
I think you're changing the buttons. No, just make the font larger.
Oh, the font larger.
So go into the new menu. The last option.
The last. Ah, yeah. Awesome. Good. We know about this. It's very good. Thank you. Yeah. So there's an intro class which has a main method called allocate. That method is running a loop on 1,000 times. All we are doing is recording, allocating 1,000 objects, how much time it takes, and we are putting out that in nanoseconds. And it jumps to a completely different figure. Alright, so let's run this. I'll go to the plus presentation. No.
Press Command 4.
Oh yeah, awesome. Thank you. Alright, so what happens in the beginning is with early iteration, like the first time it took 147,000 nanoseconds to allocate 1,000 objects, and then 53, and so the range is around 50,000, right? After right about 150, it starts to drop. Now it's 1,800 nanoseconds. It keeps going on, drops further, and well, it's around that, but sometimes it goes to even 500 nanoseconds. So there's no way that this is going to allocate 1,000 objects within that time. So it has done something. In the beginning, it started with 150,000 nanoseconds, and now it's dropped to all the way just 1,800 nanoseconds on an average. So there is. All right, so you're wondering what just happened? Like, is it just reusing the same objects again, or doing something funny? So yeah, that's what JIT is doing. Now JIT is coming to play. After a certain number of iterations, it's done some optimizations to your code, and it's reduced and improved the performance. In this case, it's more than 140,000 times better, right? 140 times better. So what is JIT? Well, it's a dynamic compiler. So as compared to C, C++, where you compile and link everything up front, ahead of time, you compared to that, this Java is more dynamic. It says, you know what, we are not going to build and compile everything. We're just going to find the hot spots in your code, which methods are getting called, which part of your code is getting repeatedly called, and we'll try and optimize that. And that's why the name hotspot, because it's trying to find hotspots and it's optimizing them. But to do that, it has to do some sort of optimizations based on something, right? Some data collected, and that's what it is. It's profile-guided optimization. As your code is running, it's finding and sort of all these stats about how your methods are performing, what are they doing, and in that process, it's creating a profile of your classes and code, and like the methods and for loops and everything. And then it goes, you know what, based on what I've collected, the data, I'm going to optimize it. In some cases, it goes even a bit further. It says, I'm going to do some aggressive optimizations. What do you mean by aggressive? It means in some cases, it will go speculative. If I don't know something, and I've only seen something, then I will just stick to it. So we'll talk about those things in further detail later. And it has, you can't just do aggressive and all these profile-guided optimization when your code starts running, when your program is up. Like it's going to be too busy doing that, right? So you don't want all your threads to block and compile the code all the time because we have so many methods and everything. So what they have done is a bit more a tiered compilation mode where you balance performance of compiler versus performance of your application. Make sure you're not hogging the resources just to compile stuff. So what are the unit of compilation? Methods and loop. So for GIT, it's only interested in like methods and loop to compile and optimize. But then it's not going to do every method. It's going to do hot methods. Hot methods are methods that are invoked many, many times. So there are some sort of thresholds that Java 8, Java 7, they all have different. And with every minor release also they fine-tune it. There's all these engineers sitting behind trying to make sure that they have a number that suits most of the applications. And all there is number of invocations to your method. If your method is called X number of times, it's treated as hot. And if we go, okay, this is a candidate now, please try and compile and optimize it. And hot loops, why not? Because in loop we are doing repetitive stuff. So we want to be able to also optimize the loop blocks. So within a method, it could be that you have 5 loops, only one of them that does more repetition. It will be optimized to by the compiler. And in some cases, it will go warm methods and warm loops. So the way it is there are all these, the decision is based on, okay, is a method hot or is a loop hot? But in some cases, you may have like a method that's called enough, but has a loop that also is iterating enough. And that means you don't want to spend a lot of that time just interpreting and executing. You want to optimize that. So this is Java 8. If you print flag, you'll see print flag final. I think you will see all the few hundreds of the parameters. The ones that I have highlighted, the ones in red are the compilation thresholds. So that's when certain level compilations are triggered. So for now, 2,000, 50,000, that's just level 3, level 4. We'll talk about this in detail. So if you're interested, what's in Java 7, or what's in, if you're using Java 9, when it comes out, do this. Print flag, see what it is. If you're interested in knowing which methods are triggered as well. All right, so before sort of going into any optimization discussions, we'll just look at what happens in JVM. So when you start, all your code is interpreted because interpreter is at work. That's what it was to begin with. Java started as an interpreter language. It said we'll go line by line. This is what we have studied, day 1 Java, right? Nothing new. But at some point it goes, hey, hang on. I think I need to compile it a little bit, right? I've been interpreting this for a while. It's like hot methods and hot loops. And it will go, okay, I'll do a compilation. And I'll start calculating profiles. So it will go, okay, if you're calling a method with a class of map, is it always a hash map or is it always a tree map? So these are basically the profile data that it's calculating and it's storing. So then it can be used later. And then that's when it makes a decision. When it has enough data, it will go, hey, I think I know enough about this. I've never seen a tree set here because nobody cares about using tree set. So everyone's using just hash map everywhere. I know that's the only type I'm going to optimize, right? And then it's going to apply all sorts of different optimizations. But there is a a back cycle. What happens if your assumption is wrong? Out of 10,000 for once you send tree set, and he goes, okay, I wasn't expecting this here. So you know what? This optimized code is not valid anymore. Let's de-optimize. So what happens when you de-optimize? Well, it's a bit expensive operation because when you de-optimize, it does stop the world de-optimization. You know, stop the world garbage collection, where full garbage collection for your stop the world, no threads are running, similar thing, but cheaper than that. Yeah. But it has to stop all the threads because it has to make sure none of the other threads are using the compiled optimized code that is now wrong. So so in case of de-optimization, you go back to interpreter and you're back to 0. So keep collecting more information and it will run the cycle. So you will see that a lot of your code, if it is behaving in this sense, would actually just keep doing these cycles. So it will perform very well at certain times and then drop back because there's an anomaly. So with JIT, they have two compilers, C1 compiler, earlier also called as client compiler. So this was made for all the Java Swing applications or anything that we write on client side. And you give a dash client option to it. And they said, you know what, if you're running on client side, you don't need you're not processing thousands of requests from anyone else. You're just doing your own thing. So yeah, this is a fast-acting compiler. It's not going to do a lot of calculations and profile-based optimizations. And it's easy to trigger more than 2,000 counts invocation to a method, and your method is a candidate for C1 compiler to go and compile. So do you remember earlier where we highlighted the red bit? So 2,000 is from there. So Java 8 also has the same for sure. And it is the code that's compiled with C1 compiler. It's up to 10 times faster than interpreter. So that's good, right? I mean, so good. 10x is really good performance improvement. And then you have C2 compiler. Very educated one, wants to make every decision right, read the books, do everything. So that's what it's doing. It's saying, you know what, I'm not just going to go and compile anyone. I'm not going to date any method. I'm just going to do when I know it's the right thing. So, which means that it needs a lot of information about the method or the loop that it has to compile. What sort of, like going back to the same thing we discussed, what sort of types types are coming in, what sort of, whether they are nulls, whether certain value is always null or not, XYZ. So and because this is a heavy compiler, right, it only invokes when your invocation count is more than 15,000 times. So if your method is called more than 15,000 times, is a candidate for C2 compiler. And it's twice as fast as C1. I've seen much faster performance. Yeah.
Is this down to JVM?
This is a JIT, it's JVM compilers. Yes. So interpreter is not a bytecode. I mean, it's going to convert. C1 is going to convert into a version of bytecode, and C2 is going to go optimize it further and convert into a different version of bytecode. No, we don't. That's why Java is a a multi-platform language. So you should be able to run the same code on your mobile as well as Linux or Windows. There is one sort of catch to it. We'll come back to that. Yeah. So okay, so we know about C1 and C2 compilers. So what about the tiered compilation? So this is like you can't just go and say, hey, every method go to C1. We know invocation. What if there are a lot of methods that are actually getting called, and you can't just again you have to make sure that there is something to not hog the resources. You can't have to be compiling all the time, right? You need to make sure there's a good balance. So that's why they have a tiered compilation. So what you want is this, all your methods to go on this path. This is the preferred path. You start from level 0, which is interpreter. You skip level 1, 2. You go to level 3. Now, level 3 is compiled with C1 method. The method compiled with C1, so it has a bytecode, but it has injected things to capture the profile data, right? And it's capturing everything. It's capturing what types it's seeing, whether it's null or not, whether it's call sites and things. We'll come back to it as well. So it's basically profiling everything. And then when it thinks it's ready, and the invocation and the method is hot enough, it will go and say, hey C2, can you please compile this method? And C2 will go, yep, I have enough information to make some assumptions and optimize it further. And that's where your method ends up in level 4. So if you have this, really good. But when the code starts, and there's always all these performance question, like what if we are not serving the actual request, and again we are just compiling. So as by now you would have realized, C1, C2 are different compilers, so they have their own queues and own threads. So that's why there is a different route as well that your method could take when C2 is busy. That means your method starts from interpreting, is enough calls, it's hot enough for C1 to compile, but C1 will go and check how big is the queue for C2. Is C2 really busy with optimizing a lot of methods? If it is, then it will go, hang on, you know what? C2 is too busy. I'm not going to capture a lot of profiling data because I don't know when C2 will get a chance to compile this method. And by that time, I don't know if what I've captured about method, the information is true or not. So it will go, you know what? I'm just going to capture some basic details. How many times the method is called? How many for loops are there? How many times they are getting executed? Simple. But then when C2 becomes a bit more light, the queue is shortened, it will go from level 2 to level 3. And that's where C2 will go, okay, that's it. Now I know that there's a chance of this method getting compiled with C2, so I'm C1, so C2. So it's just going to capture more details on everything. And then when it's hot enough, it will go to C2 and it will be optimized. Again, a good path for your methods. You want them on these two paths. Another one is trivial. Like sometimes you go getter and setters. There's not much C2 can do. They're just like very plain methods. Which is so your method that small and that trivial will go from level 0 to level 3, and C1 will realize, hang on, there's nothing here that C2 can do better than me. I've optimized it enough. That means I don't need to capture any information about this method. Let's go to level 1 where it's just compile code without any extra bits to capture information. So which means it's making sure it's faster as well. So if you have a method in level 4 is the fastest, then level 1 is the next faster, and then level 2 and 3. So if you have a lot of methods in level 3, you have like something wrong. Like maybe C2 is too busy, or they are going into C2 but they are not candidate, and C2 is going, okay, I can't optimize this. So yeah.
Sorry, it's a good question. So
Yeah.
what is it like garbage collection? Is a thread running that is doing the compilation?
No, yeah. So it's not garbage collector that does the compilation. We have a separate C1, C2 has its own compilation threads.
Yeah,
And they have their own
that
queues.
was the
Yeah.
question,
Yeah. So and that's why this tiered compilation, to balance out the performance and between the actual app.
Yeah.
Serving requests versus spending time in compilation.
Can you see them on a thread dump?
Sorry?
Can I see them on a thread dump if they're active or not?
What do you want?
thread dump?
Thread dump.
You know, you can say the GC.
There are different flags. There are different flags to set. If you want to see the outputs of C1, the compiler logs basically. They don't go in shut down and think about this. Yeah. So I'm going to talk about like how to get this information out later. All right, so let's look at some optimizations. So what sort of optimizations are we talking about? So one is, the first one we are looking at is dead code or common expression elimination. So do you see something? We ran this code before, right? And we said, oh damn, it went from 147,000 nanoseconds to just 1800. Yes, because when it got optimized, C2 thought, oh shit, this is a dead code. Why am I even executing this? I'm not going to allocate 1000 objects. So that was the 1800 nanoseconds was just the difference between the time system nano. That was the cost of system nano called twice. That's it. Pretty impressive, yeah? So in this case, it's going to go, yeah, you know what? That's not used anymore. I'm just going to compile. But remember, it's not going to happen from the beginning. It will only happen when it's hot enough. So what's dead code elimination? Oh, well, the other one is common expression elimination. So, you know, some people are very picky. They will go, oh, this supply.100 plus green is common between the two lines. Should extract it into variable. Yes, you should, if you are a good developer. If you don't worry. It will be done later. If the compiler gets to compile that method, it will find these patterns and will say, hey, you know, this is a common expression. You don't need to do it twice. You'll just do it once.
So,
yeah.
If you've got, I guess, multi-threaded code, would that change the behavior? So if you're doing the calculation up front, but you're actually expecting another thread to change it by the second statement, if you're like a crazy multi-threaded programmer?
Yes, so in that, well, if you, yes, that does come into picture. So unless you, okay, I'm going to say this, but don't be freaked out. The compilers go, if you don't have synchronized block, I'm expecting that there's only one thread. Actually, it works the other way.
Okay.
So unless, yes, if you have immutable stuff, it will optimize very quickly. And if you don't, then yes, it has to put some checks.
Okay.
But yeah, it
looks after it.
It looks after it, yeah. But again, all these only happen when your methods are fun. So so next one is something called as OSR. I don't know if you guys have heard about this, on-stack replacement. So this is what happens in case of multi-threaded environment, right? If I have two threads suppose running the same loop 1000 times, there are two threads coming in, and at some point you go, compiler C1 says, okay, this is a good enough code, goes to C2, it pushes a version of bytecode in the code cache, and then that's when it will go, hang on, the second thread coming in has to actually go onto the compiled code. So that's where it will do these like stack replacements. It will go, okay, so in case of loops, it's much more complicated because you already have a stack where you have some interpreted stuff, and then you have a for loop, and then you have some other interpreted stuff. But your loop is hot, so it's going to compile the loop and put it on the stack. So in this case, right, you know, calling it 65,000 times is a candidate. It will be compiled by C1, but it's a loop. So loop have different counters. They don't compile based on invocation of method. They compile based on the package counter. So that's, again, when you print all the flags, you will see what they are. 65,000 is for C3, level 3 C1. So for it to realize and optimize. Let's look at some more interesting things. So there's something called as loop peeling. So in the first code snippet, you can see there's a we pass an action, right? And we are then giving for each, you know, call action dot process code or something, right? Now, remember, compilers, what it's going to do, which is down here in the second line, the second snippet, is that it has to put checks, null checks for everything, right? So it will go, oh, action is getting used. Maybe it is now, or maybe not. I don't know, but I need to check. If it is, I will throw null counter exception, right? So if it puts a null check inside the loop, it's going to check for action to be null every time, which means it's wasting that time on that branch prediction for whatever is the amount of quotes. So what it's going to do is go, you know what? Why don't we move this check out and then see if the action is null or not? And if it is, then we break from there, or else we go into the loop. So this is loop peeling, which means anything that's inside the loop, all those checks that it thinks it can do outside the loop, we will peel it, get them out, do those checks, and then save you some nanoseconds. There's another one called loop inversion. Now, in this case, it's different, right? I mean, it's not same as last one. Here, you are deciding on the logger level, and then if it is a debug or not, you're going to print something. So you can't do loop, you can just go and just check outside. But here, it's going to create two branches. So each of them will have a for loop in it. Same code. That's what JIT does. It does copy paste when it can. It knows, okay, I don't want to do this is debug check. I'm going to do it once and then copy the bytecode of all this for loop inside it. And else, copy the bytecode of the other for loop inside it, which has just extra logging bit in it. Oh, good? Yeah. This one?
So the second level is it you optimize the third one because for each case the size will be concentration, right? So if there are no elements, it will never go down.
Yes.
But if it has a branch check, so everything is going to the loop, it always checks whether both sides yes or not.
Yes. Oh, yeah.
So it's kind of follows that.
Yeah, but that's okay. So, okay, I should have probably mentioned earlier. We are not looking at code's size in here. We are, yes, it will have to check the size and not null, them being not null. And because it's for each, it will have to check further things because it's inside for each. It's this instance, not null. But it's the action, right? It's the action. If your action is null, you're still going inside a for loop and doing a sec for it, and then it has to manage it. Whereas with checking that up front, with null pointer exception only once, it's gonna throw the NP. Not sure if it answers your question. Sorry.
I have to see how for each term works, but I'm pretty sure that we never go in if it goes to empty for each.
Yeah, but we're not talking about codes being empty. We're talking about action being null.
In the second snippet, we check every iteration of actions now. And just check it once. Think about the function. It iterates 10,000 times. It's 10,000 night check to save. Back in the third option, it's one more check.
Yep. And the only reason I've shown the other one is that it's doing more precautions if it is null or not. Sorry, if the codes has size or not. Otherwise, it doesn't have to even check that. So there are a few other checks it does, but we are just for loop peeling purpose. I'm just highlighting the bit that it does. Remember, this is not how the compile code looks like. It is purely bytecode. This is just a pseudo version of how it would compile into, right? If you reverse engineer that bit, it will look something like this. All right, so next one is code motion and constant folding. In this case, right, on the left, you can see we have y plus z, and it's again inside a for loop. And it thinks, oh God, that never changes, right? I'm just going to push that code motion, so I'm going to calculate that value out. And constant folding means if you have 0.1 multiplied by 35, why waste any sort of more CPU cycles? You can just actually, it can do math, basic math. When it's compiling, you can go, yeah, this means 3.5. So I'm going to calculate the value right out. Yeah, so that's sort of code motion where it has taken a value that is getting used inside, outside, calculated it once, so you don't have to calculate it again. I know they all look a bit similar, but they're doing different things. They're different purpose. One is doing null check, one is doing saving you on null check, other one is saving you on repeating the same calculations again and again, and third one is going a branch in your for loop where you're doing different things, slightly different things within for loop. All right, so coming back to earlier question, whether this is a bytecode or not, there's something called as intrinsics. Okay, So there are, I think, a set of methods that Java, when you has actually pushed native like the processor code because it has optimized them. If you think about these methods, they are very, very core to what happens at that at the machine code level. So just to make sure that we are doing the array copy and all those mat string off and everything in optimized way for your hardware. Yeah, so it does something that's not platform independent, but it's very platform specific. All right, so next one is inlining. Inlining is like a mother of optimizations, let's say that way. When you call so if you look at the first example, we have do stuff that calls process within a loop and process is doing something. If the methods are really small, right, GIT will go, hang on, this method compiled bytecode is really small. I can actually just move that method up and move the bytecode there. So I don't have to do a call site, or I mean not call site, but I don't have to switch the, add a new stack thing, whatever. So it's all within, like a more procedural way. Now, that doesn't mean that we should write all the code like that. So please don't write procedural code. Let GIT do this for you. If you do that, GIT will go, hey, this is too big. This method is too big. I'm not going to compile. Now, I know a lot of you must be thinking, what if it's a recursion? What do you do? Like, this is going to keep copying the bytecode again and again. Well, they thought about it and they said, okay, only one level of recursion is allowed. So if you're calling something a recursion, it will only copy its own bytecode only once. And then you may ask, okay, what if I have code.setDetail which calls something else, and then that calls something else? How many levels can you go in line, right? So if your method is really hot and it is inlineable, which means it's small enough, it will inline up to 9 levels. So that's pretty good, less overhead. So what are the methods that it will inline? Well, again, they need to be really small, compiled into less than 35 bytes of code. When compiled with C1, like C1, C2, it needs to be less than 35 bytes. If it is, it will inline. All right, this is a very complicated one. So we're going to look at a slightly different optimization and the problem as well. So Java, cross hierarchy analysis and inlining. So inlining is okay if you have the good candidates for inlining are static methods, constructors, getter setters. They are going to get inline like that. But what if you have a service that calls it another class which has 2 subclasses? Which one to inline, right? You can't just inline both of them over there. So for it, what Java has to do is every time you call a method where it can't identify, yes?
Right, this is for everything that it does. Does it cater it all for anything it does? This kind of stuff that is
Sorry, cater for branches?
So if you have, say, it has a switch statement.
Oh yeah, it does. Sorry. So thanks. I haven't included. I thought people will get bored about it. So yes. So when C1 goes and gets all these details and profile of your method, if it thinks that there is a certain branch you are not taking, it won't compile it, and it will put something called as uncommon trap. That's what it does all the time. It will put all these uncommon traps, and the reason so what happens? The reason of doing this is that your compiled code becomes less than 35 bytes, and if it is less than 35 bytes, you can actually inline it. So again, inlining helps compiler make decisions, understand if the variables are changing or not, and a lot of other things. So thanks for bringing it up. Yes, it does that. So yeah, in this case, right, what happens if I have a class that has 2 subclasses? When you call a method, it has to first do a discovery, right? It's called call site. It has to do a discovery of which method to get the bytecode or interpreted code or whatever it is. It has to find out which one it is, and that's in maybe around 3 or 4 extra nanoseconds of cost. But it is a cost, right? So in that case, there are some sort of different variations. So what does it mean, right? I mean, if you think about Java, JIT, class inheritance for JIT is like bad. It doesn't like it. It likes static methods. It likes small methods. It doesn't like when you have inheritance. That doesn't mean that stop doing inheritance, because then we lose this awesome feature of inheritance as well. So yeah, so that means it has to do all these extra analysis and capturing a profile to understand what it is. In the simplest case is monomorphic, which means how many of you have written interface has only one implementation? I've written so many. Yeah, so yeah, that's the monomorphic. That's what monomorphic is. You have a interface or abstract class has only one complete implementation. So when the program starts the class hierarchy analysis, we'll try to figure out how many classes or subclasses of that interface are in your class loader. If it does some sort of analysis to figure out are there any that have been loaded? Number one, no, okay. And if it can't figure out anything from there, then we go, okay, are there any that I have observed for so many times you have called this method, I always see a hash map. I never see anything else. So for it, it's like, okay, good. I'm happy with it. I am assuming we are in a monomorphic system over here for now, right? So those are good. And there is something called as bimorphic. I'm not going to go into greater detail over there, but I haven't presented here as well. So bimorphic means, yeah, you have two implementations. Why is it different to megamorphic, where you have more than two implementation of your interface or abstract class? Is that bimorphic are also optimized by compilers. It will do if and else and optimize them. So if you have a map, it will go is map instance of hash map, optimize that code, is else if it is like a tree map, optimize again. But if you put a third type in it, some people like to write new hash map and create like a class out of it and to put the values in it. Wow, that's a definite no. If anyone is doing that for performance of JIT, it's just like worse, because we use maps like crazy. When you do that, you actually are in megamorphic situations straight away, right? So what happens in case of megamorphic? It can't do inlining, it can't do branching, which means it has to perform the lookups and it has to go and spend that extra bit on it. So in this process, how I said that doesn't mean that map only has two implementation. It has more, right? We know it has more. But what it does, what JIT is going to do, when it observes only one type, it will put the uncommon trap. When it observes two types, it will put their bytecodes and put another uncommon trap. If I don't see hash map, tree map, then you know what, this method is like continuous. So that's when most of those de-optimizations are triggered by these types, which it doesn't know about. And when it encounters them, it has to de-optimize the method.
So obviously with normal good practice code, you normally want to define variables and things as their sort of high-level type. So instead of saying hash map and map, you will just say it's a map.
Yeah.
Then you assign a variable. Obviously, for the purposes of JIT, you would infer the type automatically, and you don't have to keep saying for purposes of performance or whatever, it's a hash map every single time.
No, it will. And that's why all the profile-based computations are, and that's what it is doing. But if you are then suddenly sending another one, is an anomaly. But if you're writing like one-to-one, right, one interface, one class, and if you're not going to anything, why even add this overhead on JIT, right? Let's just simplify. Is you can just use one class that doesn't need interface. But if you're going to use for mocking everything else, do encourage it. So I'm not against inheritance, please. All right, so let's have a look at this. Now this is going to be a tricky one to show with the whole presentation bit. Oh. All right. So in this case, right? Okay. Sorry. Let me just go into Alright, so we have a main method, calls another method transform. There is a class func1 which implements function, Java util function. And as every time you call transform, you're doing a sleep. The reason I'm adding sleep is that so that it gets enough time to actually perform those optimizations. Otherwise, just running this alone is not. It will never get a chance to put the optimized code in it. So just giving GIT some time, buying it some time. And then for 5,000 time, you're just calling transform.apply. The func we have sent, you're just calling apply method. Now, when you call for first 3 iteration, you're sending the same type and 5,000 times each time, package counter and everything. So that means it is going to go into hot. It is going to be treated as a hot method. So let's see what happens when you do this. So let's keep switching. So first iteration to 2.6, then about 894,000 and 413. You can see GID is at play. It's actually. You want me to go into presentation mode again? Are you guys okay? Ah, sure. Okay. Shape 4? No. Oh no, it's okay. Oh yeah, okay. Okay, do it for the next one. Alright, sorry about that. So yes, you can see the first iteration took some time because it's getting more and it's understanding what it is, and then it optimized. Maybe let's see one code. As you can see, it dropped from 2.6 to 8.4 thousand, and then to maybe C2 came into picture, it optimized it further, and it went to 413,000. So that's good. This is good performance. We are talking about good performance for your app, right? Now, what happens if we do something like this? So there is a function 2 and function 3, right? So all we are doing is, for function 2, we are going to use it. So we are going to load that class into class loader and then use it. And for function 3, we are not going to, we are just going to load, we are not going to use. Remember, we are just going to load, we are not going to use. Yeah, so yeah, first one as usual, slow. And it's 50%. Bam! See what happened? That was an anomaly, right? From monomorphic, it went bimorphic. So it did spend time. It went, hang on, I didn't see this type over here. What the hell is this func2? I don't know about this. Okay, I'm just gonna de-optimize the code, go back to it, do it again. But then you go to func3. It has optimized. Anyway, so I don't want to change the code. I've written this last minute, so sorry about that. But yeah, what's happening over there with func3 is even just declaring that, it could have gone to C2 compilation. It didn't do it because again, it's a bit slower. The only reason it's slower is because now there is another type in class loader. So the class hierarchy analysis finds a third type, and it thinks, oh, okay, I can't inline code anymore. I can't put if else. I have to always do call side. All right. Okay, so we saw some optimizations, and there's something. So these are all sort of type of speculative optimization because it's speculating. It has seen only one type. And everything. What other speculative optimization it does? I'm not going to go into detail anymore because I think people are going to just go get bored. So there's something called as implicit null assertions. So what it does is, in a nutshell, if you don't add null check yourself, right, and the method is compiled, it has never seen a null, it's fine, optimized. It sees null one time, it will go, that's okay, maybe that was just one off. I'll throw a null pointer exception. Don't need to de-optimize, right? That's just a null value. Do it twice, it will do the same. 3, yes, same. After third null pointer exception, it will go, hang on, what the hell are you doing? Why are you passing more nulls to me? This is wrong. Okay, I'm just going to add a null check. So make sure that it's a cheaper fault. So, because it has its own, all the handlers for exception, it's not going to result into a sec fault. It's just going to be a bit more cheaper. So that's type of speculative optimization. Type assertions is what we saw earlier. Depending upon what types it's saying, it's going to decide and put uncommon traps for the other types. Untaken branches, pruning, that's what we mentioned earlier. If you have a branch that's never taken, it won't create a bytecode for it, generate a bytecode for it, just put a trap, uncommon trap. And optimistic megamorphic inlining. Yes, so that's again like going back to the same, like even if there is a megamorphic situation, if it has only seen one type, it will speculative and be speculative and optimize your code. Again, there are these many other compilation sort of optimization techniques that it uses. If you are interested in any of them, there's information hard to find, but all you get is that because some of them are, actually majority of them are same techniques used by C, C++, and other compilers. So you can read wiki on them, they do same thing. Yeah, so this is what's in hotspot. So, all right, what if you want to see this? What's happening? Like like these techniques, right? There are many of them, but what if you really want to see what's happening to your app? You can do two things. One is light logging. So there's a light logging mode where it just logs bare minimum information on it. So we'll have a look at it. And there's full logging where it does a full-fledged logging of what happened to compiler, queues, how many methods got compiled, how many branches were taken and whatnot, everything. So that's a full-fledged log that writes into a separate log file.
Does the logging already affect the compilation itself because we pass another code pass to log?
It would. That's why you don't want to switch it on. So that's what I'm going to say. Don't switch it on in production all the time. When you do it, when you really, really want to analyze something and find out what's wrong. You're right. And it generates a lot of big size log files. So there are two tools available, JIT Watch, which is a Java preferred one, JIT Watch. So it basically loads the whole log file with, if you give a path to process, it will show you your code, compile code, and even the byte code as well. I recommend only do it if you are into like those sort of things. Otherwise, just stay away maybe. There is a JIT Watch IntelliJ version of it as well. So you can, when you're running code, you can ask the IntelliJ to actually get all the information and show you within your IDE what happened, which methods got inline and compiled. Sorry, and then there's another one called JMH benchmark. If you really want to benchmark your stuff and figure out what's getting optimized and what's not getting in line and how it's performing when it's in line versus not in line, if you're into that, these are more like a JUnit type. They have a lot of annotations and things you can use to capture the benchmarks. This is light logging. It looks like this. There are a lot of fields. First one is the time since this milliseconds since the compilation started. Your program started. Then there's an ID of each compilation. There are some flags, and then shows the level in which your method was compiled. Your method name and the size of the method bytecode. The flags are like whether it was a static method, whether it was native, whether it was on-stack replacement for a loop, or like found exception handler, like where it does have a lot of those weird things to make sure that if you run into just throwing null pointer exception all the time, it will optimize that as well. It'll make sure you don't get stack trace, but it will optimize it. So you don't know where it's coming from, but it'll make it perform. Yes?
Is there a way to just force your entire app to do
No, it's not possible, unfortunately. There are some future JEPs that I'll just briefly mention later. Yeah. This is if you really want to see every bit of detail with this. Switch on the log compilation and maybe give it a file. If it puts everything in your normal app log files, it's going to be really messy, and for you as well, difficult to sort of figure out what's happening. Again, these log files are really big when it dumps them in its magnitude of 200, 300 MB. So, yep, if you still want to have a look at it, particular methods and everything, do it. So what I have done, my own effort to solve this problem, I thought these tools were really crap because looking at bytecode, I don't want to look at bytecode. I just want to see what's happening to my method. That's it. And so I'm just going to do a quick demo of something that I've been working on. In my own personal time, when my two kids don't give me some time after watching Game of Thrones, so definitely not replacing Game of Thrones with this. So I've loaded a compilation log file that's in 150, 160 MB from one of our pre-production. So here it's loading it and telling you how many methods got compiled, totally 23,000, how many compiled by C1, how many compiled by C2. It's even telling you what are the top packages which has how many methods in it, and then like compiled the most. So obviously Java being the first, and then there's all these other custom packages. How many levels and how with each level how many methods were compiled in that level. There are a few things you can go and check, but then I want to you can view all the packages, how many methods were there. So look at nice graphs, simple. But then what we're interested in is finding out the methods. So you can just keep typing and it will search everything that's in the log file and it will tell you, okay, these are methods. You just go click on any one. Oh, this is a good one. So it went from 0 to 3, 4, right? So it was busy, right? C2 was busy. And then when you click on it, it tries to get this information. I have a lot of work to do because I want to find out how many inlining happened within that and system time. So if you guys are enthusiasts over here, interested in contributing, this is free. Now, what I've done is because a lot of companies are very protective about not uploading things to cloud and everything. So this is a purely JavaScript Angular 4. Irony, Angular JavaScript to analyze Java performance, but yes, that's what it is. It's come down to these days. Yeah, so it runs purely on your machine. It's going nowhere. You can switch off the internet, confirm that's the case. Or look at the code, come on. All right, back to demo. I'm not supposed to spend a lot of time. I'm already over, sorry. Just gonna finish it up very quickly now. So what do we do? What do we do next, right? I mean, as a responsible, enthusiast Java developers, because you all are here to hear me bore you guys for 1 hour. So yes, I would say exhaust all the other options. Fix memory leak, fine-tune garbage collection, fix your ORM, whatever. This is the last option. If you really have to go here, and that too if you have to go it every week, man, you have a problem. Java is not the language you should be using. Trust me, if that's the case, Java is not the language. Yep. Find out critical or most, but if you're still, sort of proactive and you want to see, like, I had to do it for certain endpoints that we had them calling millions of times in a day. So I want to make sure that they are performing right. I mean, if it gives such a good performance, why not optimize them? Why not look at them? So yes, if you have those sort of motivations, then yes, do look at the logs and see what your method is doing. That's all you need to know, at least to start with. And then you can, if it's not compiling, most of the chance is that your method is too big. And how often we see critical part written in like hundreds and hundreds of lines of code because it's too critical and called too many times. I mean, we're not going to touch this, which means we're losing on potential performance improvement right over there. Yeah, so if you're interested, do it. Capture the log, analyze them. Tool of your choice. But make sure you don't set that in production for days and days because that's really going to blow up files and everything. And yeah, fix, test, measure it again. It's like the same thing, right? We have to do the same thing. You know, fix it, run it again. Or if you have your own pre-production or environments where you can run performance tests, do that. Look at again what's the improvement. And something very easy is to write good code, write smaller methods. Let GIT do copy pasting, let GIT do inline. You don't do it because that's just going to be wrong. And if you writing very fancy Scala and all these types, sort of creating your own types all the time and everything, again, don't do that. That looks cool maybe, but it is just bad as it gets. Yeah, and static utilities. Sorry, so forgot to mention static are really good candidates for inlining if you can write static. Amazing. Yep. Sorry. For Android, well, see, Android is a different scenario, right? You're not processing thousands of requests and things, so it is allowed to be a little bit slow. Let's say that way, because you're not doing multi-threaded thing with a lot of It is applicable. It's Java, right? It is applicable. If you have a app where you really want it to be performant and on startup, maybe do some warm up. Like a lot of companies, they actually have to do this for stock exchange or anything. Would do that before the release is into production. It's done enough warm up so your JVM has compiled and done things right, not waiting for like. Yeah, 6. Yes. I think Android was on 6, Java 6. I'm not sure if they have gone to Java 7. Java 8? What, really?
Only on Android 23 and above. So kind of janky.
So I guess the question though would be more around what the actual the VM on Android. So the Dexa or what the thing that reads the Dalvik VM. Does the Dalvik VM have a C1, C2, or does it have that? Does it have other Android specific?
It could because a lot of other. Yeah. Yeah. Again, so that I think few other JRocket is not doesn't have interpret at all. It's everything is like something like that. So I don't know if it's really fast, but just saying it. Yep.
So this is probably a two-part. One is using static analysis of minify tools beforehand. So potentially you don't even need to get to JIT for something. So scripts that everything into that.
Well, it is, yes. If you, I'm just showing you techniques that if it assumes that the code is like, okay to that, and it does that. But if, as a good developer, you shouldn't allow JIT to do all this when your method is hot, right? If you know you can do it, yes, use static analysis, use everything you can up front to help JIT better optimize.
And the other part is try catch blocks. Does that have any impact on the compilers? Does it have kind of
yes, it does. It does, specifically around how you manage doing sort of. So that's what I was saying. Like if you throw too many kind of exceptions and things like when I say too many in thousands or whatever, then it will optimize that. So it is around like it is trying to do what's it's getting into each block as well. So again, it's a branch, right? Every catch is a branch. So it will try to optimize speculatively where it can. Okay, so what's next? Ooh, this is what Java is going to do, right? So I was gonna at some point talk about. I was waiting for the slide. So what's happening these days. This is what Java is doing with the compilers and what it's doing right now. But what are they up against, right? We have been dominant for quite a long time because there's a good ecosystem, a lot of frameworks, a lot of APIs, and blah blah. We have these three things coming up, which have good community support, especially Node, right? It's faster, it has good, it's a compiled language, right? So it's faster, it has good packages to do a lot of things. A lot of greenfield projects are going these days, right? So how can Java win back people to go, hey, please write your microservices with Java?
Sorry, I do here. What was Swift?
Oh, Swift, Go. So Swift is an Apple language. Yeah, Objective-C replacement. But yeah, that's Go. Google Go. That's their again backend. So and then third one is Node. Everyone's Node. So and why are we talking about? Why are we looking at this? There's one is that they are faster. They are bringing up with the ecosystem around. And second is the technology trend these days is serverless, right? Man, you say serverless, you're hired. That's it. Any recruiters over here? No? Okay. So, so everyone wants to write lambdas or Google functions, whatnot, right? But have you tried writing a AWS lambda? Have you tried running an AWS lambda with Java? How many of you have tried? How was it? The warm-up time? Really bad? Compared to Node? No? Okay. Okay, yeah. So for me, when I tried, for a lot of our services, the difference was massive from 1 or 2 seconds in Node to 30, 40 seconds in Java to just throwing it up. And if you're going to do all these optimizations and everything, as it builds and as it runs more, then you may not have that liberty or the where your container stays hot or warm all the time. At some point, AWS Lambda feature is going to just take it out. You're not calling this enough time, so we are going to save our resources and we are going to take the container out. And when it does that, you just lose everything, right? Even if it was hot or warm, whatever it was, you just lose that.
So you're not saying slow as in, you're saying more slow startup, not necessarily slow in execution.
There is, so slow, there's slow startup. Yes, that's what I'm talking about here more. The warm-up for lambdas, it is just the warm-up time. But from triggering a lambda, where to get it running, executing your code takes sometimes in magnitude of 20-30 seconds at least for us when we were doing it.
Yeah.
So,
so I guess if you've got a really heavy workload though, I mean that's where the JVM's going to start performing those other guys. Just to be clear about what the slowness we're talking about is.
Yes.
So you're going to use a JVM for more big data stuff, but you've got bigger payloads. And if you've got something that's running a long time, then that's where the JVM's going to be a candidate to use over, say Node or whatever. That's not going to optimize as much during them.
Well, for Node or others, yes, that's right. But for Node and other things, they are static. They compile and link, so they optimize differently upfront, ahead of time. It's everything ahead of time. So for C, C++, Swift, and that's why Swift has better memory management. Look, Java is my bread and butter, so I'm not saying everything. I'm just saying these are the problems Java has to deal with, right? How are you going to do warm-up issues? How are you going to fix, give you performant Java without us writing that performant code as well? Oh, okay. All right. Okay. Okay. So that's possible. The one with Java, everything is probably 8-9 months ago when they were very fresh in Sydney, and Node was very easy and very fast at that time compared to Node. But I'll do check it out. So my bad if there's something like that, please don't discount it. But I'm just saying these are the challenges as well, right? So maybe they've done something. So maybe AWS has done something. So what is Java going to do, right? It's against all these heavyweight now, soon, like coming heavyweights. They said, let's go a bit more progressive. Now it's time for us to go and optimize, have the ability to optimize your code more, analyze it more, optimize it more. But it was very difficult, or it is very difficult, because it's written in C, C++. It's very hard for them to look at the object, the graph, and traverse the graph to figure out something changed or not and everything, right? So they said, you know what? As a language, Java is awesome. You can use annotations, you can use inheritance, you can do a lot of things, right? So why not leverage Java to write the compiler optimization code? And that's what this is. It is. So they said we have a Java compiler interface, JVM compiler interface, where it's more like you have different JNI methods and you can plug Java implementation of compilers in there. Not that we write that every day, or so you can write your compiler optimizations in Java, which will do C1, C2 both. Depends upon what they have done. But this is what it is, Project Growl. So have a look at this. This is a Java 9. 8 already has it. I'm not sure if all releases, but Java 9 definitely gonna have it as an optional thing, so you can configure it.
Yeah, we'll have a talk coming up about Growl as well.
Oh, sorry about that. So, okay, moving to next one. Again, what else? We need Thor as well there. So, I mean, we need Thor and sorry, blanked out completely. Ahead of time compilation. So, what else can we do? Well, if it's going to take these methods are only going to be compiled when they are warm and everything, why not do ahead of time compilation? Some of the other versions of VM are already doing it. So this is another feature they are working on. There's a JEP reference over there. I'm not going to talk about much as well. There's a tool in Java 9 that we are going to pack with Java 9, I think. But you can compile your modules up front, right? That means they are C1 compiled, not C2. You can't do speculative optimization because there's nothing speculative, nothing no profiles. But yeah, they will compile your code in C1 using C1, but it's only restricted to Linux 64. So
it's marked very experimental.
It is. Yeah, all these are experimental features, but they have been thinking about it. Like if you think about then something like serverless, where you want to have a fast warm-up, like a faster warm-up time, whatever it is. Like you can put the compile code for at least basic Java things, not everything, but at least Java package or some of those packages, which are very crucial.
I would see ahead of time compilation and then analyze it back to the runtime. But I see the optimized version, so my method might be inline and C anymore, or do they manage to type code like API?
So C1 doesn't do inlining, I think. C2 only does it. So it's only C1 compiled. So it is not optimized like you want it, absolute end goal, but it is halfway there.
But what if I would analyze it backwards, like in the class order myself, I would see optimized it's actually different.
Is Orin for C2?
Yeah, for C1, we see a lot of optimizations on C1 origin backwards, so there might be stuff missing. I would expect it to be well.
I have again, I haven't played with this. I'm just talking about. I think there might be other people with a bit more detailed talk on this. But this is what I found. Like I wanted to find out what they're doing in this compiler space. I haven't tried it, so I don't know much about it. To be honest, to see where. But they are, from what I've understood, is C1 compiled. Yeah, that's just some info on me. I'm gonna put these slides on SlideShare and GitHub for GIT Reporter if you really feel like something that could help your organization contribute put some new features that we develop for version 1. Message me on LinkedIn or email me if you have more questions. And yeah, it's finally finished. Sorry.
So, given that we've had a lot of questions and we're running a bit late, I think we might just call it at that time. And if anyone has any questions, I'm sure Sukin would be happy to answer them after the meeting. Before we go on to our usual technology raffle prize, just wanted to open the floor up to any announcements or any hiring opportunities. If anyone wants to announce it, please have a chance.
Any meetups, any
Audiences, yeah.
So when is that one?
Yeah.
Workshops. I think I know. I think it's this lady actually. You can do better with Kotlin. Yeah, that one there. Cool.
Okay. Sorry, just last thing, not about this anymore. No GIT. There is another meetup, Google Cloud, GBG Cloud platform, which is mainly around Google Cloud. So we have another one coming on 14th September. If you like listening, I'm not going to be doing the full 1 hour talk. It's really half an hour. But I'll be talking about using Google App Engine and writing your microservices with App Engine with proper, like in Java, basically. So if you're interested, click on it.
Cool. Alright. Sorry. Just
You can use this one if you want.
what should we do? So what I'll do is I'll do the magic stop